This conference will now be recorded.
So hello guys again. So again we will now we will continue the structure of the diamond. So let's start. As I said before, in diamond, one carbon joins with 4 carbons here, and this shape is called tetrahedral. It's the same shape is in the silicon dioxide. Again, it's a tetrahedral shape which will come in the questions. Tetrahedral shape. Do not forget this, please. Just the tetrahedral shape in silicon dioxide and in diamond. So, if you will continue, what you will see, if you will millions of carbons will join with each other, we will make a Vastov network here. So this is what we call the Vastov network. So what will happen here? The giant diamond will have strong force attractions between the carbon elements, so it will make it the hardest natural substance. Hardest natural substance here. Okay, now let's continue here. Let's continue. Okay, so as we said before that millions of carbons join with each other. You know that carbon has 4 electrons. It means carbon has to make 4 bonds maximum. And as you see here that in diamond, carbon uses all its 4 electrons to make a chemical bond. So about the structure, as you see that I drew all the bonds between carbons with bold. So it means in diamond, there are strong force attractions, strong force attractions within and between the layers, within and between the layers, or between the carbons. How it happens? For example, this first layer of carbon or diamond, let's say, in one carbon joins with 4 carbons. Within the layer, there are strong force attraction. But if you will continue and make again 1, 2, 3, 4, for example, between this structure and this structure, they will be weak, strong force attraction, because we draw them with again both lines. Carbon 1, 2, 3 again. Both. If you continue, you write the same thing here. So diamond has strong force attractions within and between the layers or between the carbons. So this makes a diamond hardest natural substance. And if any substance has strong force attractions within and between the layers, so it's very difficult to break down this force attraction. So what will happen? You will need high amounts of energy to break down these bonds, so it will have high melting and boiling points. So guys, if you are writing for example a comment on the in question, so you have to give, most of these questions are 4 points, so you have to give wide answers. Yes, diamond has strong force attraction within and between the layers, so it requires high amounts of energy to break down the bonds. So because of it, or due to it, it has high melting and boiling points. Last thing, diamond cannot conduct electricity. Why it cannot conduct electricity? If you remember from the ionic bond, we said that if any material or substance, if it wants to conduct electricity, it has 2 things: freely moving ions or delocalized or free electrons. It is not ionic compound. We don't have any ion here, so we will not talk about the freely moving ions, but it is giant structure, and we will have to talk about electrons. But does diamond have any free electron here? No, because in diamond, as we said before, the carbon uses 4 electrons, 4 valence electrons, to make a bond between the other carbons. So it means it doesn't have any free electron to conduct electricity. So diamond will not conduct any electricity because it doesn't have any delocalized electrons. Please don't, in the answers, do not include this ion word. It's written here, but do not include here because it is not ionic compound. It doesn't contain any ions. This was the diamond. Let's go to the graphite. Again, I will repeat it for you. Silicon dioxide and diamond, both of them have high melting and boiling points. They are hard. What time is the hardest natural substance? Okay, and they do not conduct electricity. Okay, they do not conduct electricity. They are common or similar properties of silicon dioxide and diamond. Dioxide and diamond. So we have time. Let's continue. So what about the graphite? If you will zoom in to the structure of the graphite, what you will observe in graphite, one carbon will join with 3 carbons. So automatically, what we have to remember here, as I said before, that carbon can make 4 bonds. You can easily remember that. And that carbon has 1 free electron here. Free electron. So what does it mean? Or what is the sense of it? Carbon is a good conductor of electricity. Only non-metal which is a good conductor of electricity. Particularly how it conducts electricity, the electrons which are free electrons or delocalized electrons here, they will start to jump between the layers or within the layers, so it will conduct electricity. So let's continue. In graphite, 1 carbon joins with 3 carbons. But how graphite make its structure? Like diamond or different arrangement? Yes, exactly, it's a different arrangement. In graphite, 1 carbon makes joins with 6 carbons, so makes a hexa structure. It is the first layer. I will write for you first layer of carbons. This is the second layer, let's say. So the second layer. So what we will see here, as you see, these are the layers. As you see that I drew the bonds as it's shown in the animated PowerPoint, which I sent you. There are the bonds are between the carbons in each layer or within the layers. They are very strong. So what we can understand from here, there are strong force attractions, within the layers. Strong force attractions within the layers. But why, when we are writing with graphite, layers of the graphite slide over each other? Because there are weak force attractions between the layers of graphite. Between the layers of graphite, there are weak force attractions. Because of these weak force attractions, it is very easy to break down the layers of graphite. So what happens when we will write with the graphite? When you will write with graphite, layer of the graphite will slide over each other. Layers of graphite will slide over each other. 1 second. Layers of the graphite will slide over each other. Let's see here. So what or which type of structure we will observe here? Properties of the graphite. So what we will say about the graphite? There are weak force attraction between the layers, but within the layers there are strong force attraction within the layers, first and second layer. So because of this weak force attraction, when you write with the pencil, let's say my hands are layers of graphite, first and second layer. But when you're writing with graphite, because of this weak force attraction, the layers start to slide over each other. But in ionic bond or ionic compound, it doesn't happen. In ionic compounds, if you are applying the force, they will shatter or break down. They will make asymmetrical breakage here, not symmetrical. But in the graphite, it looks like symmetrical breakage because layers are starting to slide over each other, because of this weak force attraction. So if a molecule or structure has weak force attractions, which properties it gains. Firstly, graphite is soft and slippery. Graphite is soft and slippery. And because of this property, it is used as a lubricant. It's very important, the property of the graphite, do not forget it. And what happens when you're writing this graphite, because it comes in the questions. So what you will write down? You will write there layers of the graphite, layers of graphite, slide over each other, slide over each other. So this is the sentence or the comment which you have to write about the graphite. When we are writing with pencil, layers of the graphite slide over each other. So because we can write with it on the paper or any worksheet or something else. So layers can easily slide over each other, and because of weak force attraction are easily broken. This is why graphite is used as a lubricant. Graphite conducts electricity, as we said before, only non-metallic conducts electricity. So as you see here that in the on the wall, so it has one free electron, the localized electron. So it means that each layer has one free electron, so because it will conduct electricity very well. It is not insulator, it is good conductor of electricity. This is about the graphite. Are there allotropes of carbon? Yes, carbon, last allotrope of carbon is Buckminster fullerene. The word which we have to remember here is fullerene, because Buckminster are the names of the scientists which have discovered this spherical form of the carbon. So let's remember the fullerene. Fullerene means spherical form of the carbon, which is C60. C60 here. Okay, what makes the fullerene very different? Is the fullerene is hard and does it contain strong force attractions like diamond? Here, exactly no. Buckminster fullerene is not counted as giant structure. Buckminster fullerene is simple structure. Simple structure. Why the simple structure? So in Buckminster fullerene, one carbon makes one double and two single bonds here. It's easy to break down the double bond and the single bond here. First of this property makes the Buckminster fullerene have weak force attractions here. Buckminster fullerene consists of pentagons and the hexagon because its shape looks like football ball shape. We call it buckyballs. C60, 60 carbon join each other by using pentagons or hexagons, shape of the mass unit. So Buckminster fullerene had once two single and double bond atoms in this allotrope carbon form a shape of football. The molecules can be can be called as buckyballs. They are large, but they are not classified as giant structures. Further information you will see in the high levels. Just remember that again, it has weak force attractions. As we said, weak force attractions within and between the layers. Within and between the layers. So this makes the Buckminster fullerene or fullerene molecule simple structure, not giant. But teacher, it has a electron, but why it doesn't conduct electricity? In some question you can see this, because it doesn't matter, it has delocalized electrons. The delocalized electron in Buckminster fullerene or fullerene structure, they cannot jump through the layers, so they cannot move. They just stay in one position, so it will not conduct electricity. It is an insulator like diamonds here. Okay, this is the other form of the carbon. Do not forget, Buckminster fullerene is not giant structure. It is just simple covalent structure. For example, there are some questions here. Again, you can practice by yourself too. At home, giant covalent structures are vast of networks, covalent bonded atoms. Giant covalent structures such as blah blah blah, diamond and sand have very high melting and boiling points, are usually hard. These such things you can easily try at home for you, and after you have solved, you can check your answer is correct or not. So this is the end of our other video. So see you in the next video.